Good afternoon to all of you, and thank you organizers for giving me opportunity to share my work. So on the very first slide, what you are seeing is nanoflowers, that is made up of some material, and their application in the right side. So the first two figures, A and B, is we have taken methylene blue as a contaminants in water, and rhodamine B. And if you include these nanoflower to these contaminants, then it absorb all these contaminants on the surface, and this kinetics is very fast. Within 2 minutes you can see these adsorb on the surfaces. And the second application, I'm going to discuss about the medical application of this nanoflower. If you mix this nanoflower with some bacteria, I have shown you here only one kind of bacteria, say E. coli. Then this nanoflower interact with the surface of the bacteria, and it try to dent or puncture the membrane, and the cytoplasm will come out, and eventually the bacteria dies. Okay, and this is totally experimental work, but we have contacted ideally chemistry department for some atomistic molecular dynamic simulation, by which they can show that how these nanoparticles or nanoflowers interact with the bacterial cell membrane. Okay, so this work is mainly carried out by Rupal, who is graduating this year within 2-3 months, and I also thank the funding agencies. So all of you are aware that very limited source of fresh water we have, and even out of those are mostly contaminated by some industrial waste, mostly coming from pharmaceutical industry or textile industry, and that has a lot of impact not only on human health. We can see lots of diseases occur by the contaminants of this wastewater. So it is not limited to human health, it is also affecting aquatic health and agriculture's produce. So, so the remedy, what you can think of, the first you can think of like you can have systematic drainage system or degradation of these contaminants or proper disposal of these contaminants. But this problem is not limited only to the level of human health and all, but it also have some kind of antimicrobial resistance. Or if you just take an example of TB, then it has multi-drug resistance. So antibiotics fail to kill those bacteria. So it is maybe up to different levels. So maybe XDR or even total drug resistance. So these kind of superbugs are also very troublesome, and we suggest or we have some mechanism by which you can kill these bacteria. So I will tell you some of the important application of our synthesized nanoflower. So the talk is of two part. One is synthesis of the nanoflower and their characterization, and then the application of this nanoflower. Okay, so the choice of material is MOS2, and it has some advantage as well as some disadvantage. So advantage is this having two layers. So this 2H is always in hexagonal phase. So 2 is signing for 2 layers, and these nanomaterials are biocompatible in nature, and it has a large surface area, but it has some disadvantage of poor colloidal stability. So you have to increase the stability of this material. So by taking the octahedral phase of this material MOS2, if you mix these two phases, then it will improve some of the property like colloidal stability, and also it will be kind of conducting. So the 2H phase is semi-conducting in nature, and if you have the mixed phase, so this is kind of conducting. Okay, so very simple route of synthesis of these nanoflowers. So we have followed the set protocol of hydrothermal way of synthesizing this material. And we characterize this material with microscopy, spectroscopy, and other different techniques. And then we will learn about their application. So what you are seeing is SEM image of this nanoflower, and the typical average size of this nanoflower is around 400 nanometer. But if you look at carefully through HRTEM, then you can see some sharp edges are on the surface of the nanoflower, which act like a nano knives. And these nano knives is generating some kind of ROS, some radicals, and that interact with the bacterial membrane, and which makes a dent to the membrane and eventually kill the bacteria. So characterization part through XRD and Raman, we showed that, okay, so this material has both phases, 2H and 1T phases, and also it is mixed with the MOO3, so that gives some more colloidal stability to the nanoflower, and it is in the orthorhombic phases. So these all are available in the nanoflower. That is proved through XRD data and Raman spectrum. Through XPS analysis, you can see that the phases has more for the 1T and slightly less for 2H, and it has some contribution from the MO3. So this will give the confirmation of the presence of all these elements. For the colloidal stability, you can see the first figure is for the cytotoxicity experiment that gives you some idea about the synthesized material is biocompatible, and at a particular OD value of around 600 nanometer, it is very much stable, and you can see up to maybe 6 hours or so. Yes, I will take one more minute. And for the application part, so you can see here we have tested this nanoflower on 3 different contaminants, mostly on the methylene blue, rhodamine B, and tetracycline, so pharmaceutical contaminants. And you can see within 2 minutes of time, the signal dropped almost to 0. But we carried out the experiment up to 30 minutes, and then use just centrifuge and take out all this supernatant, and you can see, okay, so I will just skip this one, and you can see the supernatant what you collected from the vial is not having any of the contaminants. Okay. So for antibacterial activity, that can be done with two different strain of bacteria, E. coli and S. aureus, and it shows a minimum inhibitory concentration around 200 microgram per ml, and so at this concentration it is killing almost or inhibiting their growth by more than 90%. The visual micrographs is suggesting these nanoknives are making some dent on the surface of the bacterial cells, and the whatever content inside the bacteria is coming out, and eventually the bacteria is dying. Okay. So yeah, so I have contacted for the atomic stick molecular dynamics simulation how these processes are happening. Okay. Thank you. Yes.
Once
Yeah, so yes, that is another part of the, so regeneration of the nanoflower. So through some kinetics, you can, it will just unbind, or whatever ligand is bound to the nanoflower, it will just come out.
If not,
It is cheap. So easily you can synthesize 1 milligram in one day. I mean, so it will cost less than 2,000 rupees. Band structure I have not put it, but band gap I have listed for the nanoflower. It is around 2.8 electron volt. Yes, yes, it can be tuned. Uh, I have not tried.
okay, let's thank the speaker.